mechanics today, and as we have discussed in the earlier video recording about basic properties of fluid like specific density, specific weight, specific volume and specific gravity. I like to recall these because their applications are important for the further sections. Now, specific density is the ratio of mass to the volume of the fluid, and it is given as kg per meter cube. And we have the second property, that is specific weight, which is a ratio of total weight of the fluid to the volume of the fluid, and it is given by the unit Newton per meter cube. And then we have the specific volume, which is the inverse of specific density, that it is a ratio of volume to the mass of the fluid. And the last one is a specific gravity, which is the ratio of density of any fluid to the density of a reference fluid. The reference fluid right now in fluid mechanics is water, and hence we will be taking all the values of water as a reference range. Hence, specific gravity is also the ratio of density of any fluid divided by 1000, where 1000 is the density of water, 1000 kg per meter cube. Now, the next property is viscosity. Viscosity is a property by virtue of which the fluid offers resistance to the flow, or it is also called as shear deformation. Now, let's consider one example where water is flowing between section 1 to section 2 in open channel or any canal or irrigation channel. Now, if this is the depth of flow and this depth of flow could be divided into various layers, then the top layer would be moving at a higher velocity when compared to the bottom layer. Now, why is this so? Because the bottom layer is in friction at the bottom with the boundary of the open channel, while the free surface is free to move at a faster velocity and there is no friction, or it is having lesser friction. Now, the friction which is the maximum at the bottom will retard the flow, and it is having lesser velocity. Now, let's consider the friction between two layers. Suppose this is the first layer and the second one is the second layer. Between these two, there is a resistance to the flow. That is, the top layer will be moving with some velocity, but the bottom layer will be retarding this velocity. This retardation is also called as resistance to flow, or it is also called as viscosity. It is also known as shear resistance. Now, because of this resistance, a stress is created between the layers. Now, this resistance is also known as shear stress. For example, if you rub two palms against each other, you have some feel or some stress and some friction happening between the layers. Now, this is the viscosity that you have, but in fluids the viscosity is creating a larger shear stress, and this was identified by Newton, and he has given one law for viscosity. Now, this viscosity, the Newton's law of viscosity, is stated as the shear stress between any two layers of the fluid is proportional to the change in velocity between the layers and inversely proportional to the thickness of the fluid layers. If you can consider another example where we have two plates, one is a fixed plate, one more is a moving plate. Now, as you all know that when solids rub with each other, there is a friction and heat created. In order to avoid that, if we can fill a liquid or a fluid like oil which can lubricate these two plates, then this section is known as the liquid part or the lubricant part or the oil. And this section can be divided into many layers. Now the total thickness of the fluid layer is Y, and the smaller thickness of each layer is dy. In that case, if this is the thickness of the fluid layer, the top layer is going to have higher velocity and the bottom layer is going to have lower velocity because it is in touch with a fixed plate. This fixed plate is going to retard the velocity of the bottom layer. So as you can see, the velocity is quite low, and with the increase in the depth of the fluid, the velocity is going to increase because you have a moving plate at the top. Hence, the velocity at the top is high and the velocity at the bottom is low. And it also depends on what is the thickness of each layer or the total thickness of the fluid. Now, having understood this, we can also tell that the resistance between these two layers will depend on two parameters. The resistance, which is also called as viscosity, or it is also called as shear stress, is going to be proportional to the velocity between the two layers and the thickness between the two layers. Hence, Newton's law of velocity can be stated as the shear stress is directly proportional to the change in velocity, and it is also inversely proportional to the thickness of the fluid. That is, smaller the thickness of the fluid, larger the stress, or larger the thickness of the fluid, smaller the stress. Hence, it can be given as introducing the proportionality constant tau, which is the shear stress, can be given as mu into du by dy, where tau is the shear stress, mu is the dynamic viscosity, du is the change in velocity, and dy is the thickness of the fluid. Hence, mu is a proportionality constant. It is also called as dynamic viscosity, and this was derived by Newton's law of viscosity. Now, what is the unit for dynamic viscosity? Now, dynamic viscosity can be written as shear stress into the distance or the thickness divided by the velocity. We all know that shear stress is having the unit Newton per meter square, and the thickness is given in meters, and the unit for velocity is meter per second. So when you simplify the whole thing, you'll be ending up with the unit Newton second per meter square, where Newton per meter square is also called as pascals. Hence, the unit for dynamic viscosity is, in SI unit, it is Newton second per meter square, or it is also called as Pascal seconds. While in CGS unit, it is given as 9 second per centimeter square. It is also called as poise. That is poise. The conversion between the CGS unit to the SI unit is that 10 poise makes 1 Pascal second. This is required while solving problems. Now, in order to give you a feel of viscosity, as you can see in the picture, water which is having a very less viscosity of 0.1 centipoise, while honey is having a viscosity of 12,200 centipoise. Now, if you have two droplets of honey and water, and if on an inclined plane, if you drop both the droplets, which will move faster? Of course, the fluid which is having lesser viscosity will move faster than the fluid having the higher viscosity. Now, in order to also further understand, viscosity has a very wide application in industries. Now, for example, if you were to design a bulletproof vest, you would select a fluid which is having higher viscosity, because the bullet should not penetrate the body. So the vest should be made of a thicker fluid or a very highly viscous fluid. While if you were to design any fluid which were to fly high, then you would select a denser or very light fluid or a lesser viscous fluid. So industrial applications for these are very high. For example, even in 3D printing ink, we would be requiring a fluid which is less viscous but also can stick together and dry faster. So you can look into the various industrial application of viscosity. So the next concept is known as kinematic viscosity. There are two types of viscosity. First one is dynamic viscosity, which is given as mu. The second one is kinematic viscosity, which is given by the word or by the letter or by the character nu. Now, mu is the ratio of the dynamic viscosity to density. Now, what is the difference between these two viscosities? Mu, which is dynamic viscosity, deals only with respect to the shear stress and the velocity gradient, while kinematic viscosity will also tell you how the fluid is behaving with respect to the dynamic viscosity and the density of the fluid. The relationship between the dynamic viscosity and the density of the fluid is given by kinematic viscosity. Now, kinematic viscosity is given by mu by rho, but we already know that mu is given by the unit Newton second per meter square, and rho is given by the unit kg per meter cube. When you simplify this whole thing, you will end up with the unit for kinematic viscosity as meter square per second. And in CGS unit, this meter square per second is replaced by centimeter square per second, which is also called as Stokes. The conversion between the CGS unit to SI unit is 1 Stoke will be equal to 10 power minus 4 meter square per second. Again, please note that this is required for solving problems. Now, these are some of the values of dynamic viscosity. You can see some fluids which are gases like air. They have the value of 18.3 into 10 power minus 6, which is very, very, very small. That means air is not at all viscous, and that is why it is able to fly and flow and blow from one point to another very easily and very faster. Now, as you can compare it to further, like let us take glycerol. Glycerol is a very thick fluid and it is having a viscosity of 934 into 10 power 3. That is quite high. The mu value is quite high, meaning which it is very suitable for stopping any object which can flow through it. Let's understand the viscosity of water. Water is somewhere intermediate. It is having a viscosity of 0.28 into 10 power minus 3, which is having less viscosity. While you can also compare it to mercury, which is having another viscosity value of 1.53 into 10 power minus 3. Let's take peanut butter, which you use every day, and it is having a viscosity of 150. Now this was only to make you understand and feel the numbers when we define dynamic viscosity. So you should be now able to understand when I say mu is equal to 150 means higher viscosity, and mu is equal to 0.0028 is having lesser viscosity. That means the velocity with which both the fluids flow are different. And I also would like to make a note here is the viscosity depends on temperature. Higher the temperature, the viscosity will decrease. Lower the temperature, viscosity will increase. Now, based on this Newton's law of viscosity, we are going to classify various fluids. Now, why do we have to classify fluids? Fluids could be grouped together so that we can use them for particular industrial application, and we could also exploit the fluid properties to a greater extent if we know the properties very clearly. Now, this is an important question with respect to your examination. Classification of fluids. When you plot a graph of velocity gradient on the x-axis and the shear stress on the y-axis, we will have many fluids between them. Now, the x-axis can be represented by the ideal fluid, because ideal fluid is the one which has no viscosity and it is incompressible. If the mu value for ideal fluid is 0, then shear stress for the ideal fluid will also be 0. Hence, this x-axis is given by the ideal fluid. Next, the 45-degree line or the straight line passing through the origin is represented by the Newtonian fluid. Newtonian fluids are the fluids which follow the Newton's law of viscosity. That is, they will follow the equation tau is equal to mu into du by dy. Any other fluid which do not follow this equation are known as non-Newtonian fluid. For example, this dilatant fluid is a non-Newtonian fluid. The pseudoplastic fluid is a non-Newtonian fluid. The Bingham plastic is also non-Newtonian fluid. And further plastic fluids are also there. Now, if you see the graph has two extremes. One extreme being the ideal fluid with viscosity 0, and as you go towards the y-axis, the viscosity is going to increase and move towards the plastic zone. So another extreme is the plastic area. Any fluid which is having less viscous will be below the Newtonian zone, and any fluid which is having higher viscosity will be above the Newtonian zone. To understand this classification further, we can look into the table in the next slide. So you can see we have described type of fluid, the description of the fluid, the equation and the example. So the first fluid is ideal fluid. The fluid has no viscosity, then shear stress will be 0. The equation for ideal fluid is tau is equal to 0. Next one is a Newtonian fluid, the one which follows the Newtonian law of viscosity. Is given, the equation for that fluid is given as tau is equal to mu into du by dy. What is the example for Newtonian fluid? Water is a very good example for Newtonian fluid. The next classification is the non-Newtonian fluids. These do not follow the linear relationship between tau and velocity gradient. Instead, the equation for non-Newtonian fluid is tau is equal to mu into du by dy whole power n. Now, under this, if n is greater than 1, the fluid is known as dilatant fluid. If the value of n is less than 1, the fluid is known as pseudoplastic fluid. The examples of these are, for Dilatant fluid, the example is sugar solution like your sugar syrup, butter and printing ink. And for the pseudoplastic fluid, the examples are paper pulp, rubber, as well as suspension paints, the emulsion paints that you have. Then the last classification is the plastic fluid, which is above the Newtonian line. And we have two types of plastic fluids. One is known as the ideal plastic or the Bingham fluid, and the second one is the thixotropic fluid. These are again non-Newtonian fluids, and the ideal plastic follows the equation rho is equal to constant in intercept plus mu into du by dy, and the thixotropic substance follows the equation rho is equal to constant plus mu into du by dy whole power n. Again, the examples for ideal plastic is any sewage, sludge or slurry, and for thixotropic substance you can take an example of printer's ink. Now this can also be explained in sentences while you are writing the answers, or you can simply write this table and explain the whole thing. The next property going further is known as surface tension. So just to recall again, we have studied specific gravity, specific density, specific weight, specific volume and viscosity. The sixth property is surface tension. Now we all know that water behaves like a tensile membrane at the free surface. When I say tensile membrane, it offers small ductility and elasticity at the free surface to sustain some weight at the top. Now, in order to understand surface tension, you should know two words. First one is cohesion and second one is adhesion. Cohesion is the property of the substance where the attraction is stronger between same two molecules. For example, in carbon, both molecules are attracted to each other, that is known as cohesion. For example, one water molecule attracted to another water molecule will have a cohesive force. For example, another property is adhesion. Adhesion is the attraction between two different molecules. Like attraction of a paper molecule with water is a adhesion. It's not a cohesion. So cohesion is attraction between same molecule. Adhesion is attraction between two different molecules. That's why surface tension is a cohesive force. If you see the molecules, water molecules at the free surface, suppose this is a free surface, any molecule beneath the free surface is going to be attracted in all directions by the neighboring water molecule. But when you come to the top, you have the molecule at the top and there is no other water molecule to attract it at some direction at the top. Hence, the molecules around it is going to pull it down and making the free surface a little circular, and that free surface is also known as your meniscus. Meniscus is slightly curved. The reason for that is the water molecules around it are trying to pull it downward, giving a curved nature to the free surface. Now if you can see another picture here, there is a insect which can float easily on water and it can rest, and you can see its legs being floating on the water, but there is a surface which is in curved nature. This is because of the surface tension of water. The free surface is acting like a tensile membrane. So surface tension is defined as the tensile force acting at the surface of the fluid due to the cohesive force between the molecules, and it is also termed as tensile membrane or surface tension. Now to understand this further, we have three cases of surface tension where we will be dealing and finding expression for these three objects. The first one is the surface tension within a water molecule. So we have a typical water droplet or water bubble, and this water bubble, when you take a cross section of the water bubble, you have two forces acting in it. The first force is the surface tension force, which is acting at the boundary of it, and the next force is the pressure within the bubble, which will be acting inwards. So if you can see the direction of the forces, surface tension is acting outward, but the pressure inside the water bubble is acting inward. So both are counterbalancing each other. In that case, when you derive and equate the pressures and the surface tension, you will end up with the pressure inside the molecule, or the pressure inside the water bubble. P will be given as 4 sigma by D, where P is the pressure inside the bubble, sigma is the surface tension, and D is the diameter of the bubble. The second case is the case of soap bubble. Now when we have soap bubble, we will have two membranes, that is one soap membrane and the water droplet membrane. So what will happen here, the surface tension of this soap bubble will be twice, because you have two layer and two boundaries which are having surface tension, and hence it will be twice of the water bubble. That is, the pressure inside the soap bubble is given as 2 times the pressure of the water bubble. That is 2 into 4 sigma by D is also given as 8 sigma by D, again where sigma is the surface tension and D is the diameter of the soap bubble. The next case is the case of a water jet. When you have a jet of water flowing from a nozzle and it is projected to be a cylindrical jet having the length L and diameter D, then we have surface tension acting outward and the area being a rectangular projection, we will be ending up with the expression P is equal to 2 sigma by D, and this is having lesser surface tension because of the high velocity. Now these are some typical values of surface tension. For water at room temperature of 20 degrees, we have the value of 0.073 Newton per meter. Surface tension is having the unit Newton per meter, and glycerine is having 0.063. Let's look at the highest, that is blood. We have blood will be having a surface tension of 0.058. The next property of the fluid is capillarity. Now all of you would have looked at the meniscus of water and mercury. Now the meniscus of water is a downward curve, while the meniscus of mercury, which is a denser fluid, is a upward curve. Now this is because of capillarity. As I had mentioned earlier, there are two properties of intermolecular attraction between any molecules. It is known as cohesion and adhesion. Surface tension was due to cohesive force, while capillarity is due to adhesive force. Adhesive or adhesion is known as the attraction between two different molecules. In this case, when water is being there in a tube, the water molecules are attached to the molecules of the test tube. The attraction between the water molecule and the water on the test tube is stronger, and hence the meniscus will become a downward curve, while the meniscus of the mercury will be an upward curve. Now, capillarity is defined as capillary effect which causes the fluid to rise up or fall down in a small narrow test tube or narrow tubes, and the rise and fall depends on cohesive or adhesive force. This is because of adhesion being greater than cohesion. Here with mercury, cohesion is greater than adhesion. So any fluid which is having higher intermolecular attraction between the same fluid, then you will end up with the upward meniscus. But if you have a fluid having greater adhesion, where the attraction between two different molecules is there, then you will have a lower meniscus. Now this capillary rise, it can be rise or it can be fall. In a denser fluid it will be fall, in a less viscous fluid and lighter fluid it will be rise. Now capillary is given by the rise value or fall value, that is H will represent the capillarity, and H is given as 4 sigma into cos theta by gamma d. That is H is the capillary rise or fall, sigma is the surface tension, theta is the angle of contact between the molecules and the test tube. So this will become theta in case of rise, and this is theta in case of fall. And rho d or gamma is nothing but your density, and D is the diameter of the test tube. So we have discussed three new properties: viscosity, surface tension, and capillarity. Thank you.